Hello everyone. Let us begin with this today's lecture content. So far, I have received some queries from the students about the analytical approach we used to find the different load cases, different forces on the vehicle body, which was the part of Unit 4 also. So I just want to quickly recap what was the content of Unit 4. Unit 4 was basically about the discussion of few load cases, or load cases means few loads which are acting on the vehicle in different conditions, like in the static condition, in dynamic condition, while traveling straight on a path, while taking a turn, while accelerating, while braking, while moving up on a hill, while moving down on a hill. So during these conditions, different forces are acting on the vehicle body, and then we in this unit we tried to analytically calculate the different forces, the magnitude, the magnitude and the direction of these forces, and how these forces may affect the overall functioning of the vehicle. That we discussed in unit number 4. Okay, so in that unit, when the classes were on, we discussed the solution of different load cases, including the first load case, which was a vertical load case or bending load case. Then we also had discussed about torsion load case and a combined bending torsion load case that we discussed till the classes were on. Okay, and we had solved some few numericals also on these topics. And then we were discussing about the braking and the acceleration fore and aft load case. So for fore and aft load case, I had uploaded some contents earlier also, and I hope you had gone through them. So I'll just recapitulate those points about the fore and aft load case. Basically, fore and aft means braking and acceleration. So while applying brakes and acceleration, what happens to a vehicle? Okay, everyone we are familiar with the terms like momentum and inertia. So what we do while we are on applying braking or acceleration, we are changing the momentum, we are changing the inertia. Suppose you are inside a vehicle traveling at a constant speed, and suddenly a brake is applied. That means your body will try to remain in that position, will try to remain in the movement. But since the vehicle has stopped, there will be a jerk experienced by your body in the forward direction. So such type of phenomena occurs due to acceleration and load case. That is the, you can say, effect of braking on your body. But what is the effect of forces, acceleration or braking forces on the vehicle body, that we need to discuss. Okay, so when you suddenly apply a brake, the weight on the vehicle body shifts from you can say rear axle to front axle. So there will be change in the load distribution of the vehicle, and whenever there is a change in the load distribution of the vehicle, there its center of gravity may also travel, and due to center of gravity there will be whole lot of dynamic situation arises on the vehicle. So it's very critical to calculate the load distribution of the vehicle before the braking, after the braking, or before the acceleration, after the acceleration, right? So we will see during we had seen during some calculations and computations and derivations that what are the expressions for finding the load transfer or the weight transfer during braking, and similar concepts can be applied for acceleration also. So let us quickly see that. Suppose this is a vehicle, this is a car which is moving down on an hill. So you can see the road gradient. You can see the road gradient which is available, which has, I'm assuming, is as theta, and the vehicle is moving downwards. And if the vehicle is moving downwards and suddenly a brake is applied, or if the vehicle is accelerated by a retardation or acceleration value of alpha, there will be these many forces acting on the vehicle. Okay, so this is a free body diagram of a vehicle moving down on a hill, and let's say suppose the brake is applied. So a retardation of alpha is achieved on the vehicle. Okay, so due to which you can see a vertically downward force will be for the weight of the vehicle. Similarly, vertically upward force on the tires, on the wheels, the reaction forces the reaction forces. And since the vehicle is moving in this direction, so I can say is that the friction forces are also acting on this vehicle. Let's say mu into rf is the friction force for the front wheels, and similarly mu into rr are the friction force on the rear wheel. And this w, since it is placed, the vehicle is placed on an inclined path, this w can be, you can say, discategorized, or this w can be broken into two components. and one is a perpendicular component that is called as W sine theta, and a horizontal component that is called as W cos theta. Since it is theta, I hope you can find out how this will be theta. If this is theta, simple geometrical interpretations, so you do it yourself. And suddenly, if suppose suddenly the brake is applied, since the acceleration of this vehicle is decreasing, okay, so there will be due to cause of acceleration, okay, due to the generation of acceleration or deceleration, we are very much aware about Newton's second law of motion is force. A force is generated which is proportional to mass times acceleration. So there will be a braking force applied here, is that is mass times of retardation. Okay, so this is a free body diagram, and there are certain components like B is the wheelbase, the distance between front and the rear axle. X is the distance of the center of gravity from the rear axle. H is the height of center of gravity from the ground. Okay, so these are certain terminologies we are using in over here. RF is the reaction force at the front wheels. RR is the reaction force on the rear wheels. So we had derived these three cases when the brakes are applied on a vehicle. So brakes could be applied on only on the front wheels, the brakes could be applied only on the rear wheels, or the brakes can be applied on all the four wheels. So in such cases, the load supported by front and rear axles can be given by these expressions. So after braking, the load on the front and the rear wheels can be calculated using this thing, and we can calculate the load distribution, the weight distribution during the after the braking process. So a numerical based on braking or for an off-load case. See, this numerical says that you are traveling through a vehicle which is having a weight of 13 kilonewton and it has a wheelbase of 2.5 meters. Okay, wheelbase means the value of B. The center of gravity is 1.2 meter in front of the rear axle. 1.2 meter in front of the rear axle. That means this is rear axle and center of gravity. This is 1.2 meter. That means X is 1.2 meters and height of the center of gravity above the ground is 0.8 meter. Okay, so it has been said that there are brakes available on all the four wheels. Okay, and the coefficient of adhesion between the road and the wheel is 0.5. Now if the car is moving up on an inclined road, and right now it is shown moving downwards, so if I assume that if this vehicle is moving up reverse to this direction, okay, and the road gradient is given in such a way that the sign of the road gradient is 0.1. So we need to calculate the load distribution between the front and rear axle on the application due to the application of the brakes, and we also need to calculate the stopping distance if the initially before applying the brakes the vehicle is traveling at this speed 50 kilometers per hour, and we need to assume that the brakes are applied only on the rear wheels. Okay, only on the rear wheels means this expression I need to use. Okay, so let's see what we can do. So for this question, these are the given parameters: the weight of the vehicle, wheelbase, and the distance from the rear axle, or center of gravity distance from rear axle, height of center of gravity, coefficient of adhesion, and the road gradient in terms of sine theta. So for calculating the first part, load distribution, I can make use of the expressions for RR and RF for the case of the brakes applied on rear wheels. So RR and RF in that case is this expression. Okay, now here I need to find cos theta. Okay, you know, since sine theta is given 0.1 and you also know sine square theta plus cos square theta is equals to 1, so from here I can calculate cos theta is 0.99. okay, and see, we have derived these expressions assuming that the vehicle is moving down, but in this question the vehicle is moving up. So there will be a slight modification we need to do, is we will assume theta to be equal to minus theta. So theta will be converted as minus theta, so we should take theta to be negative, but it doesn't make any change over here in these expressions because cos of minus theta is also cos theta, so it will not make any change. Cos of minus theta is cos theta, and here also it is same. So the load distribution will be same if the vehicle is moving down or moving up. Okay, what will change I'll discuss in the next point. So in case of moving up or down, the load distribution will remain same. Okay, so if we substitute all the given values and these values, so I'll get the load supported on the rear axle will be 5798 newtons and load supported on the front axle will be 7136 newtons. Okay, these are the loads on the front and rear axles after the braking condition. The second part is stopping distance I need to calculate. So for the same expression, for the same case, brakes on the rear axle, rear wheels, we have also derived braking efficiency. which was given by alpha by g. Okay, so braking efficiency for this case, the expression for braking efficiency for this case was alpha by g is equals to mu into b minus x cos theta divided by b plus mu h minus sin theta. Okay, and since we have calculated, see, we know all of these values given in the problem. We have calculated cos theta also, so we will assume those values. Now here theta plays an important role. Cos of minus theta is still cos theta, but sine of minus theta is plus sine theta, so here it will add up. Okay, and since try to assume that the vehicle is moving up on a hill and you apply brake. Okay, so applying brake will increase the retardation in this case. So in this case the retardation will be increased due to sine of minus theta will be plus sine theta, so that will be added up over here. So there will be slightly greater retardation when the vehicle is moving up on a hill as compared to the vehicle moving down on a hill. Okay, I hope you understood the physics. So substituting these values, I will get alpha value nearly 3.168 meter per second square. Okay, and since the initial velocity is given to me as 50 km per hour, and if I convert this into meter per second, so this is the conversion. Now using that third equation of motion, v square minus u square is equal to 2 into acceleration into stopping distance. Okay, now acceleration is retardation here, so I'm taking a negative sign here. Right? So, and if the final velocity is 0, v is 0, I can say that u square by 2 alpha is equals to s. So that is what I have done over here, and we can calculate the stopping distance. Hope the problem is clear to you. Okay, moving on to the second question. Now in this question, instead of the movement on a inclined surface, we have been given that the vehicle is moving on a horizontal plane. There is a plain road, not an inclined road, and the brakes are applied. It is also not given on which wheels, front wheels, rear wheels, or all the four wheels the brake is applied. It is not given, right? But the things which are given to us is that the wheelbase is 5 times of the height of the center of gravity. Now if the wheelbase is 5 times the height of the center of gravity, you need to calculate the percentage of the weight transfer between rear and the front axle. How much percentage of the weight has shifted from rear to front if the coefficient of adhesion is given as 0.5. Okay, so I tried to draw the free body diagram for this case also. Again, reaction forces, if the brake is applied, this is the inertia force, mass times acceleration, and W downwards. Okay, friction forces for front and rear wheels. Okay, so in this question given is wheel base is 5 times of h. Now if the brakes are applied, there will be no retardation. If the brakes are not applied, there will be no retardation. So alpha will be 0, so this force will be 0 if the brakes are not applied and the vehicle is moving with a constant velocity v. There will be no acceleration or deceleration. Fine. So in that case there will be no retardation. But if I assume brakings and if I try to balance the moment about any axle, let's say front axle, so this will be the equation given here, that with respect to front axle, RR into B, then W by G alpha into H is equals to W into B minus X. So in this expression, in this particular expression, I have got alpha also. Okay, I have got alpha also. You can see alpha over here. Now if the brakes are not applied, this alpha should be 0. Okay, if the brakes are not applied, this alpha should be 0. See, all the terms are taken there, and this RR, the reaction force on the rear axle, or the load supported on the rear axle, is given by this expression. Now if this alpha is 0 when no brakes are applied or when the vehicle is not accelerated also, so both are true in this case. Okay, this RR will be, the load on the rear axle will be W B minus X by B. But if the brakes are applied and alpha is not 0, so the load on the rear axle will be this expression. So how much is the load transfer? The difference between these two expressions, RR dash minus RR. So that will be given by, see, this is common in both the expression. Okay, so this will be subtracted. So only thing left is this much. Okay, so since it's a reduction in weight, so there could be a negative sign, or otherwise it could be removed over here. So you can ignore this negative sign. So this is W by G alpha by alpha H by B. So W by G is mass, and we need to calculate weight transfer. So you can ignore this G value also. We need to calculate weight transfer as given in the question. You can say percentage of weight transfer. Okay. So here we have got this expression W by G alpha H by B. But since we know that alpha by G is equals to mu for a horizontal, but this is applicable only for the horizontal surface, that braking efficiency is mu. We have seen that the braking efficiency in the previous example, braking efficiency for inclined surface is this much. But for all the horizontal, all the plane surfaces, braking efficiency is always alpha by g is always equals to mu, coefficient of adhesion. Okay. So in that case, if alpha by g is mu, so I can substitute mu. So g will be removed. Sorry, this g should be removed. This g should not be there. Okay. So if g is not there, so it will become mu. This g should be removed. Okay. So alpha by g will become mu, and you know h and b, there is a relation, b is equals to 5h, so h get cancelled. So, and if I need to calculate percentage of weight transfer, so percentage of weight transfer will be like uh, change in load divided by w. Change in load divided by w will be equal to mu by 5 into 100. So that will be, mu is given 0.5 in the question, by 5 into 100, so that will be 10%. So in that case, if the brakes are applied on a flat surface, if coefficient of adhesion is 0.5, so in that case the weight transfer will be 10%. Okay. You can also simplify for such cases whenever you need to calculate the load transfer, the weight transfer on a flat surface, and if you have given mu, let's say if the mu was 0.6 and the wheelbase is 5 times of h, so 0.6 by 5, 0.7 by 5, 0.8 by 5, and if suppose if it base is b is equals to 8h, so that will be 0.5 by 8. So this is a common expression, can be used in number of problems. Okay. Now how I said that alpha by g is equals to mu? Here I have said that alpha by g, or the braking acceleration, is mu. How I have said this? Let's see by the same simple expression. Now if the vehicle is on a flat surface, on a horizontal surface here like this, okay, so in that case W is equals to vertically downward force will be equal to vertically upward force. W is equals to RF plus RR. And if I try to balance the uh, forces in the direction of the travel, let's say if the vehicle is traveling in this direction along the horizontal direction, in the horizontal direction, if I try to balance the forces, I can say W by G alpha is equals to mu RR plus mu RF friction forces. But if I take mu common, so RR plus RF will be equal to W. That is the total reaction force. So that will be equal to W. So if I cancel this W and this W, what I will get? Mu is equals to alpha by G. So for all the horizontal surfaces, in case of the horizontal surface, braking efficiency at alpha by G will always become equal to mu. Hope you understood. So I want you to solve some more problems. I will upload some more problems based on this and try to solve them. Okay. In case of doubts, do ping me, do text me on Help You Live. Waiting for your feedbacks. Thank you.